Okay, so I kind of realized that I think one of the things that I could do really is, which is going to make my life easier, and it's going to also be. Uh, do I have noise cancelling deactivated? It's just bothering me. Give me a second. No, okay, it's all good. It's all good. Okay, cool. So one of the things that I thought is that for the sake of investigating algorithms and stuff like that, I think, and investigating things using these tools, I think it would be interesting to not to keep the merging of the edges sort of automatically happening, but being sort of something that you apply as an operation, right? Say, for example, let's just run this whole thing again. So this, and then let's say that you want to have, so you stay here, right? So yeah, so that you basically kind of have, and say, system sort of like, maybe it's not merge, but it's like reduce or something like that, I can call it, right? And even like, I think it even could be interesting whether like to kind of expose the merge edges function where you would just, apply a merge to specific edges. Just because the implementation of reduce that I'll do, reduce graph, reduce, the implementation of these will just pick one specific order of edges, right? And I might just want to do this by hand. So reduce graph. So yeah, I think that is a nice. So I'll just have like maybe I should just copy these first. See if they work at all. And then really next step would be, after this is done, to move on to 3-qubit circuits where we're gonna really have hyper edges, and kind of the question here would be whether it pays off to. I have a design question which I don't know what will make, what's the best way forward, which is, I don't know if I should treat like 3-qubit hyper edges always as like a full branch, and so kind of keep the whole hyper edge, despite the fact that maybe I can, maybe the entanglement is just between two other qubits. So I think that's probably kind of going to be the next question, right? When you have multi-part, like when you have like I think to be true to the idea, I should always keep just the edges. Yeah, well, that is probably what reduce will do, right? It will actually pop things out of the edges if they're not entangled. That's what reduce should do also for 3 qubits and beyond. Yeah. But let's try. So let's see, now let's say that we want to merge these, because now we've applied twice the CX gate. So we have Q0 is in the wait, is this correct? Q0 is in the 1 state, Q0 is in the 0 state. Yeah, exactly. So that should be merged into like an equal superposition, because these are both in the 0 state, Q1. So in theory, if I just do system merge edges and I say H22 and what is this, H25 or something? Oh, yeah, those are the IDs. Yeah, merge edges makes no sense because I don't know. I really don't know what the You know what? The thing is, I should always start the. Okay, so node NB. So I should always initialize this to 0, just so I get the same IDs. This is just a technicality, right? System. Oh, can I just see the name of the edges? Node 8 and node 11. So like H8 and H11. So if I just call these by saying H8 and H11, right? Like, I don't know if this is going to be useful at the end of the day that I expose this, but at least it should allow me to test the stuff. I want to merge these things. And so, what is it doing? Merge edges. So it gets a new edge. Okay, so it actually gives it the edges, and that's not like this is still legacy code. So what we want to check is we want to get here. So we want to actually get the nodes. Node 1. So basically, no, we don't want to get the nodes. The edges have, the hyper edges have the node UIDs that they have. So so what I should do is, yeah, maybe I should so node 1 UIDs is basically self edges H1 node UIDs. Exactly. Node 2 UIDs is H2, and so for each of them, so for all the possible combinations, something's off in here though. What is it doing? So it's saying if self nodes node 1 qubit and self nodes. So if they are from the same qubit, I get I sort of make a new state out of these, which is the sum. Yeah, that's the problem, is that what happens with the amplitude, right? This is still the question. Okay, so we can address this now. We normalize the state, and then we are creating a new node, and we're adding this new node to the new edge. But we do this for all the pairs. But that's also not the right thing to do, right? No, it's fine. It's a bit unnecessary to do like this, but it's okay because we're comparing for qubits. Okay, so unmergeable edges. It's can merge. So okay, so this is using these mergeable edges. So this defines whether the edges can be merged at all, right? Because, well, there needs to be at least one element for 2 qubits, right? That's going to be complicated. So I think I'm going to have to do. So this is only for 2 qubits. So it checks whether at least one element of each edge is equal. And for 3 qubits, I'll have to check whether there's going to be max one element without or one element that's not equal, which is then the one that's merged. But it's also not true because with 3 qubits, or what you have with 3 qubits is the U. Let's see if I don't know if this is going to work out. I don't know if I have this set up properly. If I can I use Paint? Because I have these digital pen that I haven't been using for a while, and I wonder whether this works at all. It seems to work. So for 3 qubits, if we have, for example, say these 2 branches, right? That should be equivalent to 1 branch that kind of has these 2 are added together. But the truth is that the process is a bit more, because I'm trying to see, maybe I can just make it more general already. If we have the following branch set up, right? Essentially, and this is one branch, and this is another branch. Essentially, what this translates to is into just these, right? So the merge operation, it hasn't really done a merge. It's just popped this out. So maybe what this operation should do is it should go element by element and just pop things out, because it's also this is also like, it is more general, right? Because in this case you would go through the first element and say the nodes are the same, so we pop it out. Then you go through the second element and say they're the same, so you pop it out. And then basically you would have one element left, which, like, they're not the same. So you add them like these. The thing is, these can only happen. How to do that? What would be the right way to approach these? Because if I have, you know, if I just have these set up here, the merge operation should just leave it like it is. So it should say no, or even if I have, say, this setup, right? So these also should merge. So it goes through these and it says nope. Nope, so we don't merge, but then we don't add either, right? That's the trouble that I'm having is what is a condition that would allow, what is a sufficient enough condition for me to say I can add both and put them into a new edge. Also, these shouldn't be necessarily going to a new edge, right? Like my system is always going to have, like in the most generic of the ways, you can have qubits that are like in no branch, right? And then you can have entangled qubits. So kind of, yeah, these kind of setups. So it also means that the general behavior of merge shouldn't necessarily be that I make another branch out of these. It's like I should. Maybe I should label the. I think I need to label the branches with the qubits that they entangle. So I can then check that if there's no other branch with that qubit, like then it's, then I might as just well put everything back into the system edge. Because exactly, and that would allow me, that's a good idea, that would allow me to specify a merge operation not at so yeah, that would allow me to do a beautiful thing, which is so I'm gonna get rid of these. And I'm gonna call these function basically how to call these. So this should be definitely qubit 0, qubit 1. So basically, what I want to do is I want to specify simply, 2 qubits, and then let the thing do its process that I just described. So I would say merge, for example, Q0, Q1, but it's not merge edges. It's what would be the right name for this? Reduce entanglement? I can't come up with a. What is it that I'm doing? Well, I'm basically trying to reduce the entanglement. See if I can just get rid of it, right? So reduce entanglement. Reduce entanglement. So it's going to try to reduce the entanglement between the 2 qubits. I think that's a much nicer design. because then I can also specifically, take a look at an algorithm and say, okay, what if I try to reduce the entanglement here? Does the system overall become a bit more clear or intuitive, right? And maybe I should have like a sort of an expand entanglement. That I should probably have a counter, sort of the inverse operation that, like, given two qubits, I can expand the entanglement in a way that, like, it takes me back from something like from this state back to this state. So I can just, go back and forth. It just kind of distributes the thing. So again, reduce entanglement or expand entanglement. Yeah. And that's going to be a nice way to analyze the thing. Let's see, expand entanglement. Yeah. So far, returns nothing, or to do. So what this should do is it gives me the qubits, right? So first of all, I should get I wonder whether I should even really. I don't think I really need to go edge by. No, there can be multiple edges, right? There can be like 2, 3, 4, depending on the amount of qubits and depending on the type of entanglement. So I should really get a list of edges. So I did have a function here called. No, I don't have it. Okay, get edge. That those are the things there. No. Okay, cool. It's fine. I guess I need edges that have the UIDs of the nodes of these qubits, right? So I thought I had get qubit node IDs. Oh, perfect. Okay, cool. So I actually have. I should also have a get qubit edge IDs. So what this does is gives the edge IDs of all the edges that this qubit is in. Yeah. The question is, it could still be that two qubits are in sort of a non-overlapping set of edges. So I still have to double check that later. But yeah, so self edges. As I go through the edges, and now I basically go through the nodes. So node UIDs is basically self edges node UIDs. And so now I basically go for node UID in node UIDs. And I check that if self nodes node UID, so if this node UID qubit, if this node is from this qubit, then append append E. Cool. There you go. I think that's it. So is this at all being used? Oh yeah, okay. Cool, here. So now I should go here and say, I think I'm gonna comment on that so far. And then say, edge UIDs for qubit 0 are gonna be self get edge node IDs, and then we give it qubit 0, and then H1 qubit 1. Let me see if that's what I wanted to do. So it should print me the same thing for all of them. So reduce entanglement between the two qubits. System reduced entanglement. 3 were given. Well, self and cell should go here. Yeah, I think doing that refactoring was a good idea. Get qubit edge IDs. That's the edge nodes. That's what I want to have. Okay, cool. Yeah, so that gives me the edges. Now I need to get the intersection of these. I think there has to be a NumPy intersection, or yeah. Or can I just do it without NumPy? Python intersection of two lists. Only if there's an actual function that does this. Value for value in list 2, if value in list. Okay. Just like that. Yeah, then I can do this. I know it's not going to be maybe the super efficient, but we can just, don't necessarily need to convert to Python arrays and to NumPy arrays and stuff like that. Return indices array. No. That's fine. So I should. What I should do is I should. So I should basically. So the H intersect is basically, and so the value in list 1 that is also in list 2. Right? Yeah. And so the H intersect is the only thing that we care about. There we go. So now we have a list of edges to merge. And now sort of that part of the code is what I could try to reuse. Right? That I get the node UIDs. I mean, of those specific edges. Because now I would have to do. Now I'd have to do per each edge. Kind of get into these, right? So merge two specific branches. to specific edges. I think I should definitely get back. Maybe I can just copy it from. I'm too lazy. I think that is still that is still useful. I know, actually, I don't know if it's useful, the equal thing, because now we actually have these. Okay, so now we have the edges, right? So there can be multiple edges, more than two edges. But maybe let's again now just solve the case for two specific edges, right? So reduce edges, right? And here we have edge 0 and edge 1. And so that we'll just basically iterate over each possible pair. Once and now and get this thing here. So what this now? Okay, so what this should do is the following. So we should have two edges, and we should iterate over. So we can get all these nodes, and then, okay, so what's the process now? Do we, I think what we should do is we should simply, we keep popping out elements, right? And if we see, but I don't even know what the order is going to be. So, or should I count how many elements are equal and then decide? No, that's not. We should go one by one, as I said, like to kind of, so you go one by one and then decide whether you want to pop it out or not. If you pop it out, then then what? You pop it out and then you have these, and so you move to the next one and say, well, I cannot pop it out, but maybe you can pop out this one, right? So that's kind of that's a bit my worry. Maybe that is also a 0 and you can also pop it out. So, and we don't know when, so this cannot be popped out. So we leave it like this, and then we move to this one and say, oh, so this can be popped out. But we shouldn't. No, we should actually, yeah. Okay, so actually that could work. If we keep popping things out until... Okay, so maybe the logic is you keep popping things out, and if at the end you end up with just one element that is different, then that all wraps up into a new edge. And If not, then these elements that you popped out, they go to the system edge. Okay, so because this means they're not entangled anymore. So what I would do, I would get these. So I'll get the node UIDs for edge 0 and for edge 1. Then I would go through all the possible combinations and say, okay, so are these nodes equal? So I do need this equal, which I had this here implemented. Okay, yeah, first, yeah, I'll do that, but I should account for phase factors. I still don't know what to do with the amplitudes, though. This is still not clear. I might have to. So what to do? With the edge amplitudes, right? Because this is I haven't measured this in my head yet, like, because this is key to phase kickback. When you have, let me see if I can show that again with a new file. So when you have, say, for example, a branch that is like, you know, 0, 1, and another one that is 0, 0. But you know, this branch maybe has a sort of minus, you know, it has this kind of amplitude, right? Which again, this is sort of, you can take that as, for example, you know, having this wave function. Sorry. Right, and then this gets transformed into these. And so when we merge, because these elements are equal, you know, these then kind of go in here, right? So I think what the amplitudes should stay always until the very end, and then they can go in any of the node elements if there's more than one, because then these go here and turn that into like a 0 minus, right? Exactly. So I think that's the way that we should deal with these. The only trouble that I have is, can I assume that these elements are always going to be clean? No, because I can still apply a negative control knot here, a control Z, and then there's going to be a minus that comes in here. So it should still account for. I think I should still account, and I cannot pop this up here. Can I? Maybe I can. So I don't know if I should account for these, but probably I should at least keep that in mind. That that here I might still have to account for global phase factors between the states, but so far I just compare the states like these. So Exactly. So the amplitudes. Why isn't this working? Okay, so the amplitudes stay basically until the very end. That's when we decide that if there's just one node left in each branch, then we we put it in one of those. Otherwise, it stays at the edge level. So this actually, let me change the name. Is edge 0 node UIDs. Or node UIDs from edge 0, node UIDs from edge 1. So exactly. So what do I do here is I get each pair and I say factor it out. UIDs. So this is going to be where we put the nodes that have been factored out. No, I don't think that is. Because this, I'm trying to build up for already more than 2 qubits because it's going to save me a bit of time, I think, and it's helping me think in the right direction already. So definitely, I should say that if the nodes are from the same qubit, but I'm doing this wrong. Wait a second. So I'm just saying, get the edges, right? And now I know, and now I want the node UIDs of these edges. But only I want to take a look at these qubits. Right? So I'm doing this wrong. Because if I just reduce the entanglement between 2 qubits, I don't need to do all these because basically, yeah, I need to go edge by edge, but at the end of the day, all I do is I just decide whether an element pops out or not. So I'm not reducing. Oh, that's actually smart. I don't need that. I really don't need that. Wait a second, because I have the edges where they intersect. So I just need to go through each pair of edges and then check whether the nodes in there for these qubit are equal. So I need a do I need a function for this? No, I don't think I need a function for that. I think it's fine if I just do it here. So I should just go basically for edge intersect. Um, I should now go through each of the node IDs and get the ones for the qubit 0 and the one for the qubit 0 and the one for the qubit 1, which is going to be just, just one for each. So I definitely don't need that. So, and for J in edge intersect, so we will do like a double nested loop, and then basically check that if they are different, right? We would ignore the case where they are the same. We are going to, yeah, and I don't want to, I don't want to count these twice, but if that's okay, right? I start from, so it's gonna do 8 with 8, no. So 8 with 11, yeah. Then 11 with 8, yeah, we should avoid that. How can I get, because in Python and NumPy there's a way to do that. Just want to get the possible combinations. But okay, yeah, let's focus on the actual part of the code that matters, which is that once I have the two edges, what I want to do is I want to get. I'll just take care of this later. I want to get the nodes. Just want to get node 0, right, and node 1. So basically, what I would do here is I would actually iterate over the node IDs. So I'll do it here. So for n in self edges e node UIDs, if self nodes n qubit equals Q0, right? Oh yeah, I don't need to. Yeah, I wait a second. I just need to do it like this, right? So I need to iterate over each edge of this intersection, and then in each edge, iterate over all the node IDs and try to pick up. Yeah, stupid. So node 0, node 1. Then say that node 0 is node 0 UID, should stay always at the UID level, is n. If it's equal to qubit 1, it should be node 1. And really, that's it, right? So now I have for each edge, I have the node 0 UID and the node 1 UID. which are the ones that I need to compare. So these are the ones I need to compare. And now what I need to do is I need to decide whether I need to pop these out or not. There's something wrong. I think I'm missing something here. I'm missing what's going to happen. I'm missing something with the iterative part of multi-qubit, right? Because I can build. So what I can do is I can build a dictionary that says, that tells me for each edge what are the node IDs that I should check. And then I can take a look and compare these and then decide whether I pop them out or not, or by just taking a look at the different pairs of edges. But that's just going to give me let's say that I have let me work this through these again. Let's say that I have a more complicated setup, right? For example, I have 0, 0 plus 0, 1 plus 1, 0 plus and 1, 1, say plus, right? And so this is qubit 0, this is qubit 1, and this is qubit 2. Now, and the way that I would get that is by, I think, applying an x-axis control. It doesn't matter. Anyway, imagine I have these, right? So the way that I would do this is say, now I want to reduce the entanglement between qubit 0 and qubit 1, right? I want to try to see if I can do that. So I would get all these edges, and I would compare. It's like, okay, between this edge and this edge, are qubits equal? Yeah. So what do we do? What do I do? Do I pop it out? Like, what does this mean? And then and then these and these no, these and these no, this and this no, this and this no. So let's say this is branch A, B, C, and D, right? So this will be this kind of A plus B, and this is like C plus D if I do like these. And now I'll take a look at Q1, and I say that, and I'll see that I can only pop out A and C, but that is already something that I cannot do here because I've taken this specific choice already. It almost feels like there should be already an existing more abstract algorithm to do that. Because in this case, well, what I would say is, that, well, I've popped out actually this qubit already. And so now I have 0, 1, 0, 1, plus, 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 plus. But this specific choice limits me. How am I gonna process the rest of the node? So that's not clear yet. I gotta think that's something that I have to do. Put off to the next video. What is a smart way to solve these? I think I'm not far away from an ideal solution. I like these, right? So you talk qubits. So you say I want to merge the entanglement between these, two qubits. Oh, maybe I should. Yeah, okay, I should generalize that. And just give it a list of qubits, right? Qubit UIDs or qubits. Yeah. Let's just do this already for multiple qubits. It's going to be, so this is going to be just, you give it a list of qubits. But it could also be more than two, right? Yeah. And it could also be a subset of what's in the branches, right? In this case, if I would just have given Q0 and Q1, well, that would be it, right? So what does this mean? So it means that I cannot reduce because I cannot, well, I can pop these out. I cannot reduce. No. This is. I need to think about this a bit more concretely. This is not reducible. Like I cannot reduce the entanglement between Q0 and Q1, right? So this would have to account for that because I have more, left levels. I need to study these a bit more. Maybe I can. I like the way to structure it these ways. Put the qubits in here, put the edges in here, and then try to see how to solve that. Okay, cool. But that seems, at least I've come up with this design idea, which is at the qubit level, which kind of makes more sense because you don't necessarily know the edges, right? You just want to take a look at whether they can reduce entanglement between two qubits. And I don't know if I'm not happy with the name. It's not that I want to reduce, it's I just want to simplify. Maybe, what is the word? What is the, there is something in the, how was the library called? The one for the math. SymPy. Simplify expression. Maybe it's just simplify. Yeah, I think it's simplify. And expand. I've used that, so I'll call it simplify and expand. Simplify and expand. Cool. Perfect. So you try to simplify the mathematical expression or sort of the graph expression for that for the entanglement between these two qubits. Exactly. Okay, that's good. Good enough. At least I came up with a good design pattern for these, and then I just need to figure out the actual algorithm on how to do these. Yeah, because it's trickier than that. Because also these branches kind of have amplitudes associated to them, right? So yeah, I'll try to do that in the next. This will be the focus of the next probably video or two. Hope you like that.